Well, hello everyone and welcome to the first video of our Chapter 7 material. This is the chapter, the point of the course, where we start really putting together all of the things that we've been talking about all term. We've spent all term talking about sort of structure and bonding in organic molecules. We've talked a lot about about the functional groups. All those functional groups, we can measure the behavior, the chemical behavior of those functional groups by looking at things like pKa values and how they tell those pKa values, for example, tell us a lot about how a particular organic molecule behaves. We spent a little bit of time talking about how we know the structure of organic molecules in the spectroscopy section. Then we just finished up doing all of the Chapter 6 material with a little bit of Chapter 10 on the radicals. And that really was all to put together some information on how we know about what how a mechanism takes place, and what we really mean when we say the word mechanism. That is, that's our explanation for how we think a reaction is taking place. So now we start getting to use all of that information to look at some reactions themselves. We're going to focus on both substitution and elimination reactions. We're going to see how connected those two reactions are. We'll look a little bit at the mechanism of those reactions, and then we'll finish up this whole chapter with talking about how to control the reaction and decide what conditions we should use in order to get a specific outcome. And really, that's the goal of a lot of organic chemistry, is being able to look at a particular organic molecule, decide how you want to change the functional group itself, and then how to accomplish that transformation in a very selective way. So we've already talked about the concepts of regioselectivity when we were talking about the radical reactions, and so now we'll take a look at these in a little bit more detail as how they apply to things like substitutions and eliminations. So again, it's all Chapter 7 material, and what I want to do is kind of take a look at what we mean in just a very general sense when we talk about substitution reactions or elimination reactions. And so here we can start with a molecule that we would call, just in general, this would be our substrate. Okay, so that's the molecule that's going to go some kind of reaction. That's what we have in hand, and we want to do something to it in order to make it transform into some other molecule. And so just a little bit about what we're drawing on this particular molecule. What we often see here, we've got something Lg, and we'll talk about what we mean by that, but that's what we call our leaving group. And we'll talk in some more detail a little bit later about what makes a good leaving group, but in general, that good leaving group is an electronegative element of some kind. As we'll see, sometimes oxygen, sometimes one of the halides, a couple of other variations, as we'll see as we're going to kind of wrap this up at the end of the chapter material. And so this means, in general, what we see with reactions that like to undergo substitution, we're looking at substitution reactions here, undergo substitution reactions, that we have here a polar bond that is that electronegative element, typically more electronegative than carbon, because we know carbon's not a very electronegative element. So that'll be polarizing that bond towards that electronegative element, and that generates what we call here an electrophilic carbon. An electrophilic carbon, that is a carbon atom that's got a fair amount of positive character in it. That polar bond polarized towards that leaving group is pulling the electron density away from that carbon atom, making it ripe for doing some kind of chemistry, and in this case we'll see it's a substitution. Okay? Now, what about the rest of this particular reaction? Here we've kind of defined some of the electronegative element. We've got the polar bond, the electrophilic carbon. Now, the other thing that we have that comes in here, and I'll just draw this in a general sense here, and I'll put it with a negative charge. So that, in general, is our nucleophile, and I think we may have introduced this term a couple of lectures a long time back when we were kind of looking a little bit at carbonyls and just kind of understanding a bit of their chemistry, but we'll see this a lot here again. So it's this is a nucleophile, so it's an element that's got a lone pair of electrons on it, something that can share those electrons to form a new covalent bond. It may or may not be charged. Right, so many elements, if they've got a lone pair of electrons, often carry a negative charge on them, but also we'll see lots of examples of nucleophiles that are neutral atoms that come in and act as a very good, very strong nucleophile anyway, even though they've got a lone pair available to do this. And so that nucleophile may or may not be charged, and then we can displace that, use that nucleophile to displace that leaving group. So we can come in with that nucleophile, displace the leaving group. That leaving group may or may not be charged in some case, but here what we're really doing is we're substituting one functional group for another, one element for another, and we usually do this in a solvent of some kind. And so what we're going to do in a couple of lectures, a couple of videos from now, is we're going to look at all of these parameters in a substitution reaction and look at how we can alter these parameters to control the outcome of these particular reactions. And so now what we're going to take a look at next is then if we're comparing substitution, we want to compare that to an elimination reaction. Okay, so what we have here now would be a typical substrate that we might imagine using for an elimination reaction. Again, this is the substrate. The substrate is what we're starting with, the thing we're going to carry out our chemical reaction on. Again, we've got a leaving group, again, typically an electronegative element, and here again, of course, we've got a polar bond. And I'll point it out because it's important. It's important for us to be able to recognize what the polar bond is, where it is on our molecule, because recognizing that polar bond allows us to decide what kind of chemistry we can do on that particular molecule. And of course, it's typically easy to recognize those leaving groups are often those electronegative elements that we're really familiar with, so it's easy to be able to see that. And then what we have happening with an elimination here is that we also have a base now. And that's usually a charged molecule, although in some cases a base doesn't necessarily have to have a charge on it, but it typically can carry a charge, but at least must have a lone pair of electrons. And that lone pair of electrons has to act as a proton acceptor to remove a proton from our substrate. And of course, explicitly drawn out one of the protons here to kind of give us a hint that maybe that's the one that's going to be eliminated in this case. So now, what's the product of this look like? The product of this looks like, oh, I'll do this in black so we don't get confused here. So we have the leaving group, typically is a charged leaving group. In some cases it's not necessarily, but it can be typically a charged leaving group. And what we've done is we've eliminated that molecule, that HLG, off of the substrate itself. And of course we do this all in some kind of solvent. And for now, we'll just leave that as something in general. We'll take a look at very specifically at what kind of molecules, what kind of things we use as solvents, and how we can use them a little bit to control the outcome of the reaction here. And so we're eliminating the elements of HLG in this particular case from our molecule. So let's take a look at an example reaction here. So here's a typical molecule that we might imagine as a substrate. We've got an alkyl halide of some kind, and of course we spent a bit of time talking about how to make alkyl halides. We'll talk some other time about how to selectively make a secondary alkyl halide, but we've got an alkyl halide here that we can use as a substrate. And now we've got a molecule that we're using as something that might act either as a nucleophile or as a base. And so here, and of course I'll just draw them in, which I haven't yet, so I'll draw in the lone pairs, just to remind us that there's lone pairs there. Again, this particular molecule is charged. The oxygen's got a full formal negative charge, and I put the sodium counter ion in there just for the sake of it. And I've drawn a solvent underneath, and again, we'll talk in some more detail in a later video about what solvent we'd use and how we could use that solvent to potentially influence the outcome. And so now if we imagine what the outcome might be of this reaction, we've got here again our leaving group, of course, is that electronegative bromine. That's our leaving group. Relatively electronegative, it'll polarize that bond. There's our polar bond. So we might imagine, at least in one of the outcomes of this particular reaction, is that we might just simply substitute that bromine with the OET, with the ethoxide anion coming in. Of course, that ethoxide anion is the conjugate base of ethanol. So we might just displace that. And I'll just draw that up here just to give me some space to draw in the other potential outcomes. And we'll talk in some more detail about how this would happen, what the mechanism of this kind of reaction would be, and how we know a little bit about how this takes place. But there we've just simply displaced the bromine with the ethoxide. And so that's the substitution reaction. And now we might imagine that we have a couple of elimination products as well. And now I've drawn explicitly out this one hydrogen atom over here, this green one. That hydrogen atom there, we could imagine, for example, O-ethoxide, that ethoxide anion removing that proton, acting as a base. And we know ethoxide anion is the conjugate base of a pretty poor acid, pK of 16 for ethanol. That's not a very strong acid at all. So that's a conjugate base of a very weak acid, makes a relatively strong base. So we can imagine it removing that green proton and giving us an elimination product by taking those and leaving a double bond behind. Right, removing that particular proton, and that proton would go on to the ethanol. But now there's, of course, if you're taking a careful look at this molecule, you're seeing that there's another potential proton that we could remove here. There's this proton here in purple. So that purple underlying proton could also be removed from this particular substrate by the O-ethoxide anion. So there's nothing stopping that ethoxide anion from removing that. But let me draw the elimination product, and then we'll take a look a little bit about how to potentially make some at least preliminary guesses about what might be the outcome of this particular reaction. Okay, so there's removing that particular proton, the purple one, giving us that elimination product there. So now here, this is really, and we spent quite a bit of time talking about this in the radical section, here this is a whole question of what we've been calling regioselectivity. So regioselectivity, look, we've got three possible outcomes for this reaction. We've got the substitution product where we just displace the bromide with the ethoxide anion. And we've got two possible elimination products where we remove a proton and leave a double bond behind. And so now what we're going to spend a lot of time talking about is being able to try and decide how we would come about to see what we could imagine the outcome for these kinds of reactions. And so just one of the things that I'll point out here at this stage is if we look, for example, at the two elimination products, we'll come back to the substitution product a little bit later, but if we look at these two elimination products, we can already make some very educated guesses about the potential outcome of this reaction. Because again, and I'll just redraw them here on a clean piece of paper. So there, I'll redraw them on a clean sheet here, and we can take a look at those molecules. And we said quite some time ago, we got an entire video that we posted up on the stability of alkenes way back when we were introducing functional groups. So if you don't remember that, go back and take a look at that, because we said in that video that in general, more substituted double bonds are more stable. And so we've got two different choices about the relative substitution of these bonds. We've got this molecule on the bottom here, where there's only one substitution, in this molecule on the top up here that's got three substitutions around that double bond, far more substituted than the other alternative. So just based on what we know about double bond energies alone, we'd be able to say that this one would be more stable so more stable versus less stable, and so we can use a little bit of our knowledge of the mechanism to think about how to control the outcome of this. And already we might be thinking a little bit back to what we were talking about earlier in some earlier videos about things like how to control reactions that have more than one possible outcome. Okay, so for what we want to do next is just take a very brief look at the mechanism of these reactions. And we'll take a look at the mechanism of those reactions in our next video.